And we'll get to our last speaker for the day. This is Takehiro Yoshioka. He's going to be talking about mapping the spatially inhomogeneous cosmic reionization with Subaru hyper Suprime-Cam.
Can you see my screen?
Yes.
All right. Thank you for introduction. Hi everyone. My name is Takehiro Yoshioka. I'm a graduate student at University of Tokyo. Today I'd like to talk about mapping the spatially inhomogeneous cosmic reionization with Subaru HSC. One of the important features of cosmic reionization is its spatially inhomogeneous nature. Reionization of neutral hydrogen proceeded gradually from the surrounding of the newly formed objects, and the H2 regions formed the bubble-like structure as shown in the right picture. This reionization topology is determined by several parameters such as the distribution of ionizing sources, ionizing photon escape fraction, and the density of an intergalactic medium. So investigation of reionization topology is important for studying these parameters. Lyman fraction is one of the widely used methods to investigate reionization. The Lyman fraction is defined as the fraction of Lyman-Blake galaxies that show Lyman emission lines. Right figure shows the Lyman fraction as a function of redshift. The Lyman fraction increases from redshift 4 to 6, partly due to the less dust content of high redshift galaxies. On the other hand, Lyman fraction decreases rapidly at above redshift 6. This sharp drop is thought to be a signature of reionization. Although the Lyman fraction is a good probe of reionization, the Lyman fraction measurements in the previous studies require spectroscopic observations. As a result, it is much difficult to obtain large sample sizes. Therefore, those studies can only determine the average neutral fraction of the universe, and they cannot investigate the spatially inhomogeneous reionization. To overcome this problem, we use Subaru Hyper Suprime-Cam HSC. HSC has a very wide field of view, enough to detect inhomogeneous reionization, as shown in the right figure. From this wide field of observations with HSC, we can efficiently detect LAEs and LBGs. Taking advantage of this unique feature of HSC, we aim to observe for the first time spatially inhomogeneous reionization by efficient survey of LAEs and LBGs at redshift 6.6. Then we describe our observations and samples, the galaxy samples we use. We use imaging data on the 1.5 square degrees UD cosmos field taken by HSC SSP. We detect LAEs at redshift 6.6 on the flux excess based on the flux excess in narrowband filter as shown in this color magnitude diagram. And we obtain 189 LAEs. Then we detect LBGs at redshift 6.6 by using the Lyman-Blake technique as shown in this two-color diagram. And we obtain 179 LBGs. One important thing here is that we have to detect LAEs and LBGs at the same redshift to probe reionization. For this purpose, we use the newly installed intermediate band filter IB945. The filter transmission curve is shown in the top right figure. IB945 makes it possible to detect LAEs and LBGs simultaneously at the same redshift, 6.6. The selection functions of our samples are shown in the bottom right figure. Though the width of LBG selection function is wider than that of LAEs, it is much narrower than that of typical Z dropout sections. from the selection function, we find that using IB945 can achieve selecting LBGs at almost the same redshift as LAEs. As we select LAEs and LBGs separately, the redshift range and limiting magnitude of them are not the same. But to correct these differences, we apply these selection functions and limiting magnitudes to a simulation model when we calculate the neutral fraction. Please note that our methodology is a bit different from the typical Lyman fraction with spectroscopic observations. Using the selection criteria described in the previous slide, we calculate the selection completeness of LAEs and LBGs by molecular simulations. After the completeness correction, we find that the surface densities of our sample are consistent with previous studies. Here we calculate the density distributions of LAEs and LBGs. The black dots indicate the position of the LAEs and LBGs, and the background color maps indicate the overdensity. Next, we estimate the neutral fraction of the universe from the observed LAE to LBG number ratio. After the completeness correction, the LAE to LBG number ratio is found to be 0.76 plus minus 0.1. Here we use a simulation model of Inoue et al. To estimate the neutral fraction. In the simulation model, they find a correlation between number ratio and neutral fraction, as shown in this figure. This simulation model is a combination of large-scale n-body simulation and radiative hydrodynamic simulation, and it computes dark matter density, ionizing photoradiative transfer through the IDM, and galaxy formation. By using this relationship, the average neutral fraction in the field of view is estimated to be less than 0.4 from the observed number ratio. Now our results are consistent with the previous studies. Next, we show the spatial distribution of LAE to LBG number ratio. In the field of view, the variation of number ratio is a factor of 3. And this difference may reflect the spatially inhomogeneity of cosmic reionization. It implies that the reionization is in progress where LA density is high. On the other hand, reionization is delayed where LA density is low. But this variation may be due to the intrinsic distribution of galaxies. So we will discuss it later in our talk. The scatter spatial variation of LA to LBG number ratio is shown in these red marks. However, as seen in this figure, the uncertainty of the number ratio is large due to the shallow depths of our observation. So we cannot give a strict constraint on the neutral fraction. Unfortunately, we cannot detect the spatially inhomogeneous reionization. Then we discuss one problem that must be considered to detect the spatially inhomogeneity of reionization. Because the number of galaxies also depends on the large-scale structure, the variation in the number ratio may be due to the intrinsic large-scale structure without IgM absorption. The right figure shows the scatter of number ratio with IgM absorption as a function of aperture size within which we calculate the number ratio. In this figure, we find that the scatter of LA to LBG ratio is large in the smaller aperture size. So we find that a large aperture size is necessary for this aim. To distinguish a reionization topology from the large-scale structure, we compare the scatter of number ratio with and without IgM absorption in the simulation data. And we find that the scatter with IgM absorption is slightly larger than that without IgM. We think this difference is aroused from the reionization topology. However, this difference is not significant, so we find that it is hard to distinguish them even with much deeper observations than our current survey. Finally, we calculate the Lyman alpha equivalent width and compare the equivalent width distribution between high and low, between LAs in high LA density regions, shown in blue, and LAs in low LA density regions, shown in orange. We find that LAs in high LA density regions more populate higher equivalent widths. From this figure, low LA density region implies higher neutral fraction, while the statistical significance is not sufficient. In summary, we attempted to investigate for the first time the spatially inhomogeneous reionization from the efficient survey with Subaru HSC. We found that mapping the spatially inhomogeneous reionization requires much deeper imaging, and that it is difficult to distinguish the reionization topology from the large-scale structure. That's all. Thank you.
Thank you, Takehiro. We'll wait just a minute to see if we get any questions.
Okay, have you measured a two-point correlation function of LAEs and LBGs?
Not, I haven't measured it, but I think it's interesting.
I'll just ask, can you say any more about how the model you use sort of populates the intrinsic Lyman alpha luminosity of galaxies?
Okay. About the reionization simulation, we use a combination of hydrodynamic simulation and n-body simulation. In the simulation model, they use a typical model for simulate Lyman alpha emission line. So Lyman emission line is determined by the halo mass. Lyman alpha luminosity is correlate with halo mass as shown in this figure. And from this simulation reproduces the Lyman alpha luminosity function, autocorrelation function, and LA fraction of the observations in the literature.
So do you plan to observe other extragalactic fields with the IB945 filter?
No, we don't plan to other fields with IB945.
Right, that's, there's one more question, we'll do one more. So it looked like you had a region at the top center, which was overdense in LBGs, yet had few LAEs. Does this still fit into the reionization picture, or is this consistent with scatter?
Here, about this figure. overdense in LBGs. Top center here. I don't find any inconsistency with reionization picture, but I think it's interesting the LA dense distribution and LB distribution is different at almost the same redshift. That's clear. I don't know that's the clear answer for the question.
We'll let the questioner follow up in the Slack if they like.
Okay.
Thank you very much for your talk, Takehiro, and thank you to all the speakers in sessions 4 and 4B, and 3 and 3B while we're at it today. Today was a long day. So we hope that you will join us tomorrow at 13:30 UTC for the final 2 sessions of SAZERAC. We will see you all then. Have a good rest of your day.